Good afternoon, everyone. So today's session is on the creation of the mask file using the Clevin. So before I start with the tool, so let me go to the design. So till date, am I audible to everyone?
Yes, ma'am.
Okay,
Yes.
okay. Let me share my screen. Is the screen visible to you? You participants, can
Yes, yes,
anyone?
ma'am. Yes,
Yes.
yes.
Okay. Okay. So what we have done is till date we have taken one example that is MEMS accelerometer, where we have shown the steps from this design till the how exactly we extract the information on the change in the capacitance. So, referring to the same model, we will be taking the today's session, which is on the Clevin software, wherein we are going to see how exactly we create the mask file uh, for the design. So we know that basically COMSOL is a mod design and a simulation tool. So wherein we cannot give the same file for the fabrication, we just have to create something called as a mask file or the which is in the format of GDS or SIF. That has to be given for the foundry. So basically, COMSOL cannot create a mask file directly from the design. Okay, there are few more tools such as IntelliFab, IntelliSuite, or Coventerware, which are basically MEMS CAD tools to virtually prototype each individual process steps, and that builds a 3D model for the resulting structures. But we have to, it is a licensed one, so we need to pay a huge amount to procure that software tool wherein we can create a 3D model directly with the help of the process design layers. But in order to create the mask file in a simplest way, we have another tool which is called as a Clevin, and we will share that RAR file or the zip file in the group so that you can all start using the Clevin whenever you want to create a mask file. Okay, so from the structure, we know that we have to create a mask file, and that mask file has to be in the form of either GDS or SIF. So GDS is basically a binary format, graphical data stream format, and SIF is a Caltech intermediate form, which is in the form of ASCII format. So we can have our design in the form of a mask file which contains the information regarding the structure, that is the shape of the structure, rectangular, circular, or the triangular, or whichever the structure design you do in the MEMS software. The same structural information has to be given for the foundry in the form of GDS or SIF file. So in order to create the GDS of this, we know that basically this is the proof mass, okay, and the proof mass has interdigitated electrodes for the capacitive sensing or for the comb drive sensing, okay, and we have another side a contact pad wherein again we have fixed electrodes, right, which will help us in sensing the change in the capacitance for the applied acceleration. So we know that this is the device layer which has to be in the silicon material, and we see here the space which are in white in color is basically a trench. That means uh, we know that there is a SOI standard process flow. I'll just show that PPT to you, but just for your understanding, we should actually create something called as a trench, wherein this this silicon layer, which is a device layer, is not attached to the substrate and it is free to move whenever we apply external force or acceleration. So we know that there should be a space wherein this proof mass along with the IDTs are free to move. Okay, and it is not constrained by the substrate. And we need to create a trench wherever it is made free. Okay, that means in this areas, right, we can see that the electrode should move and the electrode should not be attached to the substrate. So in these areas, we basically include something called as trench. Okay, so now let us take a review on little basic aspects of the creation of the mask. Okay, so what we have here is the given area for the designer. So I hope now there is a group that is made uh, through the IEEE activity, wherein we have a leader and the mentor assigned to each group, and the each group is given with the defined area for their design, that is about 8.5 9 mm by 9 mm, but the best fit is within 8.5 mm and 8.5 mm, that is 8500 micrometer into 8500 micrometer is the area given to you for your design. Okay, so within this area we need to fit our the structure or the sensor or the actuator, whatever we have designed, that should be well fitted within 8.5 mm and 8.5 mm area. Okay, so next, we can see there are few layers which are important here. So this is one cross-section view of the soil substrate, wherein we have the substrate here, okay, and which is of 400 micrometer thickness, and we have a oxide layer which is an insulator whose thickness is about 2 micrometer. Okay, then this is the color which is in blue is the device area or the silicon area wherein we are going to create the device structures, right? And then we have the two metal layer. So one is a pad metal. Wherever we have the contact pads, then we use a pad metal. And wherever it is complete, if the information I have to take entirely from the diaphragm, let us consider from a larger area, then I have to go for a blanket metal. Okay, going ahead, so this is a cross sectional view of the structure, wherein we see that this is the substrate, the one in the gray color is the substrate, and one with the kind of black is the insulator, and the blue is the silicon device area we can see, and these yellow color one are blank metal and blanket metal and the pad metal. Okay, so as I said, if I have to have a structure which has to move freely, then I should separate it from the substrate. Okay, so there should be a region wherein it can move freely within the given area. So I have to create a trench here. This is called as a trench. So the portion wherever I have to remove the substrate area is called as a trench. So we have to define a layer, particular layer when we design in the Clevin tool, which defines, okay, this particular area I have to remove the substrate area, and that is called as a trench. Okay, so basically we can see there are 5 layers. So the blanket metal is 0.65 micrometer. This is the thickness of the metal, where 600 is the thickness of the gold, and 50 micrometer 0.05, that is 15 nanometer is the thickness of the chrome metal, and we have the oxide layer which is of 200 micrometer, and mainly the silicon, which is the device layer, is should be of 25 micrometer. So in your design, whenever you do a geometry using the XY plane, that is a work plane, and you have to extrude with the thickness of 25 micrometer. So this is important. So all your designs should be having a thickness of 25 micrometer. This is only our concern. The rest of the things are taken care by the fabrication. Only our main concern is on taking the silicon device layer of 25 micrometer. Okay, please make sure when you design or when you do some calculation, that is modeling, please take the thickness of 25 micrometer in all your design aspects. Okay, going to these are given by the foundry. So each layer, what is the thickness, minimum thickness, and their tolerance level. And then what is the resistance that is defined for a particular material. Okay, so this is ohms per centimeter or a square meter that is given here. So just remember that pad metal thickness is of 520 0.52 micrometer. Okay, and silicon is 25 micrometer, substrate is of 400 micrometer, and the blanket metal is 0.65 micrometer. Okay, so we are not worried much about other material other than silicon, because design is the main motto of the MEMS, the training, wherein we have to take the silicon thickness as 25 micrometer. Okay, so all this design, we need to take few layers for our design, right? So one is the pad metal. Okay, then the silicon. Then we have something called a soy hole, which is which can directly define the region if there is a diaphragm wherein we have included few hole structures. Okay, then instead of defining the silicon and within the structures a hole, circular hole, we can directly tell the foundry that if with the help of a soy hole, that there is a soy hole layer, the mask layer itself that is present, which can easily create a hole structures in the soy device layer. Okay, so we should know the pad metal. Okay, that is important. Wherever we have the contact pads, we need to use a pad metal layer. Then silicon is for the creation of the device layer, and soy hole is if we require to include some hole structures in the diaphragm or this any structure, then we can define directly with the help of a layer called a soy hole layer. And then in order to remove a certain area below the device area to make the structure entirely free to move, then we need to create a trench region. And then if I have to extract the information from a larger area, then I need to go for a blanket metal. For example, a parallel plate capacitance, wherein the capacitance is taken over the entire area of the diaphragm, then I can go with just a blanket metal. Okay. Uh, Going ahead, so we know the layers which are important for creating the mask well, that is pad metal, soy hole, trench, and the blanket metal. So depending on our design, we need to choose the required layers. Okay, so these layers are given with some terminologies. Okay, or the numbers. So if we are using a SIF format, then they are defined by a short letters like pad metal. It is for pad metal. And silicon device layer is defined by SOI. And if there is a soy hole, then we take by typing the name soy hole. That particular layer is taken by defining the name of that particular layer. Whereas if we are creating the mask file in the form of a GDS, then there are 0 to 255 different layers that exist in the tool. We need to use a defined layer number. For example, if I'm using a pad metal, then I have to use a GDS number of 5. And if I'm using a soy layer for the structure, then I have to take that particular layer by giving a number 10 out of the 0 to 255 layers that is available in the tool. Okay. Similarly, the trench 20. Okay, so make sure if you with what type of mask file you're going to create, whether it is a SIF format or the GDS format. If it is a SIF format, then you have to define the layer information with the help of their nicknames or the mask name. And if it is a GDS format, then you have to call the layers or add the each layer information by giving the numbers to that numbers that defines that particular layer. Okay. And we can say one more thing here, minimum feature size. So minimum geometries should be used whenever it is necessary. For example, for a SOI, the minimum feature size that is defined is 3 micrometer. That means we can go up to as small as 3 micrometer, measurement. Okay, thickness, or the width or the length, provided they are of highly sensitive design. So that means we have to have that 3 micrometer for our better results, better analysis. Only then it is better to go with the 3 micrometer. Otherwise it is always better to have greater than 3 micrometer as the minimum feature size. That means out of available structure what you have, the minimum feature size should not go less than 3 micrometer. That is another important point to remember. One is the thickness. Next one is the minimum feature size of the soil layer. It should be always greater than 3 micrometer in your designs. Okay. And there is something called as minimum space. That means whenever you have a particular pad metal, okay, this distance between the metal and the silicon, if they are, since we know that from here, okay, this is the silicon layer above which we are going to keep the metal layer. So whenever we have the metal layer, we should make sure that from the silicon to the metal layer there should be a certain gap which is important to maintain from the fabrication point. Okay, so that is what shown here. That is minimum of 3 micrometers. So it is better to keep certain distance between the 2 3 different layers which we are using, so that there is no overlap, because we are going to create a trench. Let us consider we are going to create a trench, okay, in the soil device layer. Then we should keep a distance or the gap between the trench and the silicon as 3 micrometer. Okay, it should not overlap exactly on the same point. Okay, I'll just show that in the next upcoming set slides. Okay, just a second. There is some disturbance. Okay, so that is one thing. So I was mentioning there is some minimum feature size and there is a minimum gap that has to be kept in our mind when we design the structures in the Clevin, or when we create the mask file in the Clevin tool. Okay. So one more point to remember is whenever we use the beam, let us consider a simple beam here. Okay. If the width of the beam is greater than 600 micrometer, okay, then we don't have any worries in our design. But whenever the width, right, we can say this as the width. So whenever, if the width of the beam, right, width of the beam, if it is less than 6 micrometer, then the maximum length of this beam, okay, this the length, right, beam, okay, if it is anchored at one end, then it should not exceed 100 micrometer. Otherwise, it would curl up. There is a high chance that it would curl up. So it may not give the required results later on. So one thing to remember, whenever we have a beam, if its thickness is less than 6 micrometer, then maximum length I can have is how much? 100 micrometer. Whereas if the beam thickness is less than 600 micrometer and it is anchored in both the sides, then we can go up to 500 micrometer as the length of the structure, okay, or length of the beam. Okay, and one more thing from this figure, what we can notice, so here we have the beam. Okay, let us consider this is a simple beam which are connected to the anchors, right, with certain angle, that is right angle of 90 degree, correct? So the angle of and the angle difference between the contact pad, we can say it is a anchor wherein we are going to give the contact pad, and this beam is exactly 90 degree. Okay, then there is a high chance that they may result in a cracking after the fabrications. Okay, so make sure when you design, this is not preferred. When you create a mask file, there should not be any beam which is having exactly 90-degree angle at any point of the structure. Okay, so because it will result in the cracking when you create, do the etching, when you create some trench structures, wherein you have to remove certain material from beneath this. Okay, in such case, if I have a 90-degree difference, or the angle between the structures, then there is a cracking which may result in the after fabrication, so it may not work function exactly as our requirement. So what we have to do is, so there are two more variants, you can see this and see this. Okay, wherein we give kind of a beveled structure, wherever there is a structure with 90-degree angle. Right, so you can see here, so they provide a kind of better support than this, but the best one is the fillets. So you can see here, so in this area they have included a fillet structure, which will not actually vary the design aspect much, because it is only at little variation or little mass has been increased than this, so it will not actually result in much difference in the functionality. Because okay, but if at all you keep a right angle at the corners, then there is a high chance that during the etching, where we use a dry etching, there is a certain portion of this may get trenched. So instead of being like this, there is a chance that it may remove our area from here. So what you get is, see, you can see, or the beam becomes weaker, right? So there is a high chance that at this point also the certain amount of silicon may be removed. So this beam actually becomes weaker, right? So here it is, thick, wherever here it is thin, right? So this is the one more thing to remember, that whenever we are using creating a mask file, make sure you are creating a fillet like this to avoid the cracking or the breakage of the beams. Okay, so is that clear to everyone till here? So basically, we have to go from the COMSOL tool to another tool, which is a Clevin tool. Okay. And in the Clevin tool, it is directly creation of the mask file by taking few layers that is available in the tool. Basically, there are 0 to 255 layers that is available, but out of which we are in the requirement of only few layers that is dependent on our design. So for a simple accelerometer, we are basically going with three layers, that is pad metal, soy, and the trench. Okay, whose number are defined by 5, 10, and 50. Okay, so remember we have to take only three layers for our design in the Clement. And one more thing, we cannot have a more than 100 micrometer length if the thickness, or thickness is nothing but the width here, I would say, because thickness is defined by the thickness of the soil layer, which is already set as 25 micrometer. But if we are going to have a structure, a beam, if the width of the structure is less than 6 micrometer, and it is, if it is fixed only at one end, anchored at one end, then we cannot go beyond 100 micrometer length. But if it is anchored at both the sides, then it is possible to have up to 500 micrometer as the length of the structure. Okay, and in order to avoid the cracking, okay, or rolling up of the the structure beam, okay, we have to use something called as a fillet, right? So in order to avoid cracking during fabrication, because we are going to remove certain portion in some designs wherein when we do with the help of deep reactive ion etching, during which there is a high chance that the area wherein we have exactly 90-degree angle, such structures may also be removed during the etching process. So in order to safeguard these structures, we basically go with adding the fillet. So we can also use the beveled corners, but the best way is to include the fillet structures wherever we have 90-degree phase shift phase angle between two different structures. Okay. Now let us move ahead with uh, drawing or creating the mask file for a simple cantilever, simple accelerometer. So we can see here, this is a proof mass, okay, which is anchored at the anchor. So these are the four anchors with the help of a simple parallel beam suspension, okay, and we have connected the electrodes. So these are basically moving electrodes which are present on the proof mass, right? And then we have another set of electrodes which are fixed electrodes which are again connected to the anchor. So similar to this structure, right? Similar to this structure. So this is the proof mass which is connected to the anchors here. Okay. And this is the fixed set of anchors where we have fixed electrodes which are connected. And this is how we can see whenever there is no acceleration, they are at the fixed position with the two different distances. But whenever when you apply some force or acceleration, basically the proof mass moves, and along with the proof mass, the connected electrodes moves, as because of which the gap between the electrodes vary, and that will result in the change in the capacitance, right? So we need to know this entire structure, right, is of which layer? Can anyone answer? This entire structure should be made of which layer? Anybody? Which layer it should be made of? Silicon. Correct. Somebody answered. Yes, we have to go with using the silicon layer as the device layer, and we need to have trench wherever it is free to move. Correct. So I'll just show one file. Okay. So can you all see here? So basically the green color one. So I'll take you to through this step by step. Just before we start, let me show this so that something is known to you before you start, right? So as I said, you have to use three different layers. One is the soil layer, which is layer 10. Okay. Then we have a layer 5, which is a pad metal. So I'll just disable everything. So this is the soil layer where we have the complete design or the structure, device structure. Okay. Then we have a metal, which is a pad metal, which are given to the contact pads with the number 5. So you can see layer 5 is basically a pad metal. Layer 10 is basically a soil silicon device layer. Okay. Then what we have is a layer 20, which is a trench. See all of you here, whenever I enabled this, so basically, I don't know, this is only the device area. So I should define where exactly I need to remove a certain, area which is on the substrate beneath this structure so that the structure is free to move, right? So see here. So only at this places, right? So I'll just so here I need to remove the areas, right? This should be made free. The spring should be made free. The proof mask should be made free. That is why I create a trench so that during the fabrication, the mask layer related to the trench defines that this area, under this area, I need to remove the substrate layer. Okay, so that this entire structure is free to move whenever I apply external force or the acceleration. And one more thing I was telling about is the minimum geometry size that is relevant to these fine structures. Okay, now as of now, they're not much, smaller. We can just check. See, it is 842, somewhere around 830, so somewhere around 10 micrometer width. So it is not a problem. I don't have any restriction on the structure or the size, okay, on the length. Only if it is less than 6 micrometer, then I should be careful about the structure. Okay, then coming to this is the trench, this is the device. So we have to keep a minimum of 3 micrometer gap so that during the fabrication, I do not remove the device layer also. So one thing we should remember that we should keep a distance or the gap between the device layer and the trench. Minimum is 3. So for the best, we can at least keep 3 to 5 micrometer distance so that they do not overlap. Otherwise, this may lead to fabrication wherein a certain portion of the device layer also may be etched during the fabrication. Okay. And one more thing, see here, this is basically a pad metal. So I'll just remove this. So this is basically a pad metal which is put on the silicon. Okay, here also I should make sure that, see, 2300, 2303. That means 3 micrometer gap. When I create the mask file, I should make sure that they do not overlap exactly on the same point. Okay. And one more thing, see here, there is no fillet being added. So this may result in the cracking of the structures after the fabrication. So the best one would be creating a fillet like this, right? So we have to create a fillet wherever we have a sharp edge so that it do not break after the fabrication, because we have to reuse it for multiple times, right? We are basically using it to bring out some product. So in order to avoid such things, we need to include a fillet. Okay. So I hope this is understood. One thing, I need to take a layer. So let us is do the design. Okay. Just remember, we need to take few layers. We need to keep some minimum distance between the layers so that it do not overlap and cause the cause the removal of the device layer during the fabrication, during the etching process. And one more thing to say is mm, okay, whenever I start the design, I'll tell that point. So I hope this is now known to you, right? This is basically a mask file of a simple accelerometer with the different suspension they have used. Okay, so now let us create one simple, mask for our design to understand how to use the tool. So basically, we will share this tool. Okay, Clevin is the tool that we are going to use. We will share this tool along across the mail. Okay, so and so I'm just opening the GUI. So I create new. Okay, so this is my the complete mask. You can see this is a 5-inch mask and this is a 4-inch wafer. Okay, so the area of this mask, this device or the silicon wafer is 4-inch because I'm using a 5-inch mask. So there is a possibility to change the mask size as per your requirement. Okay, you can change 3 inch, 4 inch, 5 into up to whatever the inch wafer you want to use, you can use. But only thing is for us, the area is given to us. This is 8.5 mm by 8.5 mm. Within that, we have to do our design, right? So I have to create a new file. So I created a file new, right? And then this is giving a 5 inch mask with the 4 inch wafer. Then if I see on the leftmost corner, this is the edit objects. So this is for the selection. And then if I have to edit few nodes, so out of a square, if I want to move one of or two nodes to the next point, right? Then I can select and edit that particular node. Okay. Then zoom option. Then if I have to create a rectangular or square, I have a direct option. It is similar to a paint. Okay. So this is rectangle. And if I want to create some polygons of random shape, I can use a polygon. So if I want to use a wire for the routing purpose connection, then I can use a wire. So circles. So arc. If I want to use a text, to rename my file, my group, my college, anything. So I can have a text file wherein I can write something, okay, my name, right? And then comes this is not so important, scale. So if I have to exactly measure and create the structures, then I can use the scale for the same. Okay. I have taken a mask. Okay. I know these are the tools available for me to design the structure. Then what I have to do is basically I have to add the layers. So I'll just remove all the layers. So even to remove also, I need to define which area I need to remove, which, see, 0, pad metal 20, and then it's 20. Oh, it's pad metal is 5. Okay. So now I removed since scale is okay. So now I removed layer. So it is a blank model now. So first thing I need to go to layout. Okay. I can choose the grid setup wherein I can define what is the minimum, grid spacing. So here I've set 100. You can change it to your requirement. So you would have designed some structures, and depending on the structure where you want to exactly position, or where exactly what is the dimension. If it is having 125 micrometer, then you should create a minimum of 25 micrometer as the grid spacing. And if it is fine, if all the layers are more than 100 multiples of 100, then you can have just 100 micrometer as the uh, size of the grid. Okay. Then, so as of now, I'll keep 100 micrometer. That is the grid spacing. See, I can zoom in, right? So 3600, 100 spacing. There is a 100, each point is on the 100 micrometer spacing. Okay. Then I have to add the layers, right? So I go to add layers. So I have to use layer number 5 for the pad metal, right? It has been added. Then another layer is layer 10 for the soil. So I'm adding layer 10. So you can see indices from 0 to 250. So out of 255 layers, I need only 3 different layers for my design to create the mask. Okay. So pin 8. Okay. Then layout, add layer. It is 20. Okay. So this is in the form of JDS. But if I want to have no in the form of SIF, so I need to have names, right? So, or we can, if the file I have created in the GDS by taking numbers, if If I save it in the SIF, then I may not or the fabrication foundry may not understand the layer information. So in such case, it's better you rename it. Okay. So go to layer properties. Layer 5 is basically pad metal. So PMETL. Okay. And I can choose their shape, their structures, color, everything. Okay. Then layer 10 is basically properties. It is basically a SOI device layer. Okay. Then layer 10, 20 is trench. TRCH. Okay. So I now define the layers. Now, before I start, it's better I fix the area within which I have to create the structure. Okay. So what I do, so it's always I go with the easiest way is to go with zero positioning because we can easily define their x and y coordinates. So I'll just go to zero. I see just go here and click. So it creates a line marker. So here also I go and create a line. So exactly this is now 0, 0 position. And the given area is how much for us? It is 8,000 by or 8.5 by 8.5 or 9 mm within 9 mm. So what I can do is I can create a marker here and one more here. So this is my area wherein I have to create the structure. So this is my area for you all. So please initially fix the area within which you're going to create your design so that you don't get lost in understanding or defining their dimensions or structures. Okay. So now I can use just a minute. Okay. So this is the structure. So basically I need a square diaphragm with the beams, parallel beams that are connected to the anchors. So we will start with the design. Okay, I'm just taking a random value. Okay. Uh, so let me consider this is okay 3,000. So I'll and okay, let me fix within this area. I'm going to create my design somewhere at the center. Okay. So what do I do? This is how much 1,000 micrometer along the X and here along the Y also 1,000. So basically it is 1,000 micrometer uh, area of the proof mass. So I have to use the soil layer, right? So select the, so you are not requiring any other layers as of now. It is only soil layer. So choose the soil layer and take the rectangle. So this is my the proof mass. Okay, now I have to create an anchor. So that's another point I wanted to say before. So whenever I create, the beam and which has to be connected to the anchors, I should not create any structure exactly at this point. For example, okay, you can see here, this is again will lead to some fabrication error. So it is better to have a 50 micrometer gap 50 micrometer gap from the edge. So please remember this. You cannot have anything on exactly touching exactly on the end points here. There should be a minimum of 50 micrometer above which you need to create your beam. For example, okay. So this is my, beam. I will define the dimension. Okay. So this point is exactly 400, 4,000, and this is X. Okay. And this is X1, Y1, this is X2, Y2. So 4,000, and this should be somewhere 4,100. Okay. Then, so 100 micrometer is the thickness. So let me consider now, since I'm drawing the uh, parallel beam for the suspension, let me use some, this is as per your design, but just for the rough, view of this mask well, I'm just taking a random value. Okay. Don't take exactly this. This is depending on, these dimensions are depending on your design. Okay. Just for understanding this tool, I'm just taking a random value 4,000 to 4,500. That is 500 meter. Is the This is X. This is X2. Okay. And then this is 3,000. This is Y1. This is Y2. So this is what I was telling. 3,050 to 4,000. Okay. This is how you need to have the, uh, a gap is what I was saying. Don't connect exactly at this, because during the trench, there is a high chance that some of the soil area may get deleted, or I mean etched. Okay. So better to keep a certain area gap. Okay. See, this is 500, and from here, it's basically gap of 50. So you can see here also. So 3,000, and it is above. You can see this is 3,050. Okay. Now I have to create a contact pad. So I do a contact pad. Okay. So I can just take the soil and create a contact pad. So again, this contact pad dimension is given by the foundry. So sometimes it is better to have 200 micrometer into 200 micrometer as the dimension of the contact pad, wherein we are going to coat this metal layer, that is a pad metal. Okay. We can define its, properties, that is dimension. So as I said, this is X1, this is X2. So we need to have 200 micrometer as the dimension. Okay. So now with the help of this, we can just create a mirror option similar to a console. Even this provides some, simple way where we can create the mirror. We can create the arrays. Okay. So what we have to do is we have to select this. Okay. Right click, transform, mirror. So exactly, since we have taken this position at 0, okay, it is somewhere around 3,000. So half of it, right? 1,500, 3,000 and 4,000. So 3,500 is the center point, okay, wherein it has to mirror along the horizontal, right? And also along the vertical. So let us do first one. We'll do it on the horizontal. Click on the leave original. So you have created. Now again, select, transform, mirror along the vertical. Along the vertical is again how much? It is 3,500. Right? Again mirror. So the structure is ready. Okay. Similarly, you can create now all the IDT, interdigitated electrons, within the, as per your design. Okay. Similar to this, right? You can create this IDT structures within that. Okay. And then I was telling you about the creation of the fillet. So this is what I was telling. This is not acceptable. Okay. And also here, right? This is also not acceptable. So we have to create basically a fillet. Okay. So how to create a fillet? Take arc, insert arc. Okay. Fine. Take somewhere, right? Copy this, copy. Okay. And paste it. It is actually rotated. See, this is how you can do it. So you will have to do it on every corner wherever it has a straight cut, 90-degree angle. Okay. This is another point which is important. Then, so I'll not just go through the complete structure because it is simple as paint. You can just create a rectangle and you can create a mirror wherein you can define the number of arrays. So for example, I'll just show one. So this is what, okay, properties. Okay, so this is basically from this electrode, right? These are the anchors. This is the electrode. So all these electrode dimension has to be taken from your COMSOL dimension. Okay, so you can just go to the properties and change their dimension. Okay, 4100.
Hello, ma'am.
Yes.
Is it possible to export the two-dimensional geometry from
No,
console and
no. It's not possible because it is completely a layer information, Uma. So the input is only the layer and the structure. So there is no in this tool it is not possible. Whereas in the as I mentioned in the beginning, the Coventerware or the IntelliSuite, there it is possible. There you directly take the
okay.
layers and simulate. That is
Okay.
kind of a similar approach to the fabricated device, whereas this is only creation of the mask. So from your
Okay.
dimension, from your structure, you are just taking the information about each structure. Okay, and then you are
Okay.
defining the size. Okay,
Oh, okay.
so it is not possible to import any structures here.
Okay. Two-dimensional structure also it's not possible.
No,
Dot
no,
.bxf file is not
no,
possible.
ma'am.
Okay.
As per our knowledge and information, we have just tried with all the possible. So it is only because the layer information, it is in the geometry, there is no layer information. But here it is, we have to define that layer and we should mention as, how is the structure, right?
Okay.
So that is why it is not possible.
Okay.
We have to do it here. It takes little time because this is, we have to create the trench to every point, these fillets, creation of the trench and the dimension of 3 micrometer gap. All those points are little careful because otherwise, even if the device simulation is correct, if the mask file is not created in the right format, then high chance of the device failure. Maybe you again it will be at the cost of so much money and so much effort on from everyone. So please make sure you follow these minimum criteria, minimum geometry rules, minimum gap that has to be considered when you create the geometry. So you can, as I said, you can create the mirror you can scale, right?
Okay, okay.
So this is possible, right? So you can rotate, you can increase the angle, you can mirror, right? You can move the structure, and also you can edit and let's see.
And some Boolean operation is also possible.
Yes, yes, moving option is possible, and we
Boolean
can
Boolean
duplicate.
functions.
You can see here
Yeah.
duplicate option. So we can create an array with rows and columns and spacing. Okay, so with this we can duplicate the structure, so that will ease our work. Okay, then so this is mask creation. Then we have to use a metal wherever we have to give the contact. So basically these are the contact pads, right, where we have to give the contact. So this, see, this is what is not acceptable. So we have to have a minimum of 3 micrometer gap as a minimum requirement. So what you can do is you can select this, go to the properties and choose 4497, right? So everywhere, just reduce the scale so that it is having a certain gap. Okay. Similarly here, 700. So it is 697, right? So everywhere, wherever you have, it is 3,997. Or else what you can do is you can just use the scale. Okay. You can measure the gap between them. It's too small. So, or you can use with the help of this cursor. See, this is at 4,500 and this is 4,497. So likewise, you need to also have a 3 micrometer gap here. So 3, somewhere it is, see, 4,000 here. So you need to have a gap of somewhere 3 micrometer, and this should be below that. Okay, the pad metal should not completely cover the device layer. Okay, so this we should ensure. The next one is taking a trench. So I just enable this. Okay, so I need to know where exactly I need to remove the material. So this entire portion I need to put a trench, right? And I should make sure that here also I need to have a gap. Okay. Okay. So X1 this is, so from 2500 is 2503. Okay. This is X2. So X2, it's fine. I'm not worried now. Let's see this. See, there is a gap. Okay. Like this, you have to be little careful when you do a complete structure, because there is a high chance that this may get overlapped, and which may fail to function after the fabrication. So please make sure of where exactly you are going to create a metal, what should be the gap between the device layer and the metal, and also the trench. Okay, so similarly here, 4,500, 4496. See, and that is from the device. So I need to create 94. See, again. So 3 micrometer from here to here, 3 micrometer from this device layer. So these are the few points you need to be careful when you create a mask file. So I hope you got little insight on this, right? Uh, just try to, so after your design, try to get the details of each, the coordinate, basically their dimension of each structure, note down, and then it is easy to go ahead with the creation of the mask file. Okay. We will share this tool or the software through the mail. Okay, then create, how to save this is file. Okay, then save as. So in this, there are two ways. One is GDS format or SIF format. Okay, so give some name and then save it. Right? So it takes time, a little more time when you start, but when you get used to it, it is easier. Okay, it is only the practice. So the practice as the the practice makes man perfect. So the practice makes the design perfect here. So please practice the tool. First, this is all the second part of the design. The first part is always try to choose as of now, since there is a group that is formed. So please try to choose a apt design. Discuss among yourself to come up with the best design that is possible. Uh, Follow the design rules that is taught in the session. Create the design, simulate, check, verify, and then once it functions correctly, then only go with the Clevin and create the mask. Otherwise, it takes a lot of time to design the create the mask file in the Clevin. So please take only after the final decision on your design. Okay, and once after you verify the design functionality is perfect, right? Modeling is perfect. Only then you can go for the Clevin and create the mask file. Okay. Any doubts? So I think that is all for today's session. There are two queries in the chat box. One is which one is GDS2 and other is SIF. It is SIF, not SIF. It is CIF. Okay. And the other doubt is how the layer numbers are decided. So these is basically given by the foundry. So the tool, it has all the layers that is defined. So based on the foundry, they will define these are the layer requirement. So they will tell you which layers to be used, and that is already defined in the tool. Okay, you can use that. So for further details, you can go through this website. So we will share the link of this website wherein the complete information, whatever I just conveyed, is present here. Okay. So this is the layer numbers are defined, already defined in the tool, and that is defined as per the requirement of the fab. Okay. Any other doubt?
Ma'am,
Yes, ma'am.
from where I should download that console setup file?
From iSTEM, ma'am.
I still I'm not getting where it is exactly located. Just
No,
that
initially you have to register and they will
I
provide
did
you.
I did
Yeah.
that and all, ma'am. This thing is status is allocated. Console software status is allocated. But
Okay.
we have to download that set of file, no? From some.
Yes.
Yeah.
Yes.
Yeah. From where is exactly?
Ma'am, in the whatever the information they have shared, they have given the guidelines, is what I suppose. They have given all the
Yes.
guidelines.
They
No?
have given the guidelines. In that, they
Yes.
have said like you have to download that which one. This
You can go to Comsol website and try to download because they would have given which version. So you can just type the version and download and give the whatever the information given by the license, maybe the license uh, by the ISTEM. So you can also contact them if you have any clarification, ma'am. If you need any further clarification, you can contact them. They are very much approachable.
Thank you.
Yes, ma'am. Thank you.